Hello everyone, myself Dr. Santanu Kundu. I welcome you all to this lecture of soft computing techniques. This is the fourth lecture of Module 8. In the last lecture, we have seen NSGA-II with the help of some numerical examples. Today we will try to solve few more numerical questions. So let's try to understand NSGA-II algorithm once more. So in this algorithm, first step is that we need to assume some parent populations. We need to assume some parent populations PT. From there, we select some parents and then we'll do the crossover mutation and we'll find child population, that is QT. Now we'll assume RT equal to PT union QT. So now after RT, we perform a non-dominant sorting to RT and identify different fronts. So we have seen that we last class we identify fronts, so if both are minimized, then this is F1, this is F2 and so on. Step 2, set a new populations PT plus 1 equal to 5 and set a counter I equal to 1 until the number of elements present in PT plus 1 and number of elements present in front I less than equal to n, then we perform pt plus 1 equal to pt plus 1 union fi and increase I equal to 1. So now if it is not true, then we need to perform the crowding distance mechanism. We will perform the crowding sort and include the most widely spread, that is the crowding distance value is more. So we include the most widely spread n minus pt plus 1 solutions by using the crowding distance values in sorted fi to pt plus 1. We need to sorted fi to pt plus 1. Step 4, create offspring populations qt plus 1 from this pt plus 1 by using tournament selections, that is either the rank, if rank is less we will select, or crowd distance is more we will select. So that is tournament selection, then crossover and mutation operator will create new populations. So one example of NSGA-II, here we are solving one question which is minimize f1 equal to x1, minimize f2 equal to 1 plus x2 by x1. X1 lies belongs to 0 to 1 and x2 0 to 3. So from the entire range we will select some initial solution, that is solution number 1, 2, 3, 4, 5, 6. Here x1 is 0.31, x2 is 0.89. Here x1 is 0.41, x2 is 1.92, x1 is 0.22, x2 is 0.56, x4 is 0.59, and here the value of x2 is 3.63. At 5, x1 is 0.66, x2 is 1.41, at 6, these things. Now f1 is equal to x1, so these values will be the same. Now f2 will be 1 plus x2 by x1. So that will be here 1 plus x2, so 1 plus 0.89 by x1, so that is 0.31 something, it is 6.10. So we calculate f2. Similarly calculate f2 for x1 x2 value of solution 2. So here for solution 2 f2 will be something like 1 plus x2, so that is 1 plus 1.92 by 0.41, so that is 6.79 and so on. So that is for initial population. Now from here we do the crossover and mutation. We'll do the solution A, B, C, D, E, F. So here x1 0.21, x2 0.24. For B, x1 is 0.79, x2 is 2.14. For C, x1 is 0.51, x2 is 2.32. For D, x1 is 0.27, x2 is 0.87. For E, 0.58, 1.62. F is 0.24 and x2 is 1.05. F1 is the same. F2 can be calculated like by the same formula, 1 plus x2 by x1. So we have calculated F1 and F2. So we have total 12 populations. So now from the RT, we will try to find the Pareto front. So just like F1, F2 and so on. So this plot is applicable only for 2 dimensions. There is different algorithm for Pareto front. So you try to understand that comparison method what I taught in the last class. So here we try to do the same. So try to understand here. So here is that both are minimized. So see which value is less here. So that will be in the first one. So I think less is 2 point, less is for A. So here you will get the less value at A. Then definitely 3, D1, E5 here and so on. So let's see the front here. So first front is 5 comma A comma E. So here check it. So here these are the fronts. So one more method in this diagram you can check like that. So where is both minimize. So put a place a paper like that. So minimize here na. So that is signify this side minimum and down signify this side minimum. So move the paper, keep the paper in this direction and move it. So see here there is no point is here. So A is not dominating by anyone. Similarly 5 and E will be not dominating by anyone. So in the front one you will get 5 comma A comma E. In front 2 you will get 1 comma 3 comma B comma D, and front 2 you will get it 2 comma C comma F, and there you will get front 4 you will get F4. So these are the some concept. Now this is the for step 1. Step 1 is that there is RT is there, we create fronts. From RT we get Pareto fronts. So now step 2, initially PT plus 1 equal to null set. For I equal to 1, PT plus 1, that is front 1 is 5 comma A comma E. So number element is 3. So here initially PT was 0, then so next to do the next iteration for I equal to 2. So already PT plus 1 is 3. So F2 equal to 4. So we need to calculate crowd distance. So elements from less crowded area of the front are preferred. So here as you have seen that in RT there are 12 populations. So for the next step, which is PT plus 1, we need to select 6 populations. And another 6 will come from crossover and mutation. So we need to select 6 populations. So another 6 will come from QT plus 1. So now already there are 3 selected, 5 comma A comma E. Now from 1, 3, B, D, we need to select another 3. So we will apply the crowd distance formula. So here that is the value of 1, 3, BD. So F1 value is 0.31. If for 1, F2 is 6.10. For 3, F1 is 0.22. F2 is 7.09. For B, F1 is 0.79. F2 is 3.97. For D, F1 is 0.27 and F2 is 6.93. Here the maximum value of F1 is 0.83 and minimum value is 0.21. For F2 maximum value is 8.54, minimum value is 3.61. So we need to write F1 by doing ascending order. So ascending order for F1 is first is minimum 3, then D, then 1, then B. ascending order for F2, that is first is B, then it is 1, then it is D, then it is 3. So here 3 and B are in the boundary region. So here we can say the crowd distance is infinite. I mean B and 3 are selected. Okay. So and initially front 1, 5, comma A, comma E, these are selected. So there is only one vacant place, and this place can be filled by either D or 1. Which crowd distance is more will be selected. So we need to do the crowd distance. So as I told you that here, if if we want to do the crowd distance for solution D, then D is I. So this is xi minus 1, this is xi plus 1. For F2, D here is I, so 1 is xi minus 1 and 3 is xi plus 1. So here the first formula is that crowd distance for F1, so the value of xi plus 1, that is 1, the value of 1, so that is 0.31, and for 3 that is 0.22, so 0.31 minus 0.22 by maximum minus minimum, so that is F1. So that, and for F2 D is I, so you will get this value 1 is xi minus 1, 3 is xi plus 1, so 3 is xi plus 1, that is 7.09, xi minus 1 is 1, so that is 6.10, that is again it is maximum minus minimum, so that will be 0.31 minus 0.22, 0.83 minus 0.21. So you can write this is equal to f xi plus 1 for 1, and it is f 1 xi minus 1. So this value here x plus 1, as I say that this is 1 and xi minus 1 is 3, so that value is taken here, similarly here also. So the crowd distance is 0.347. Similarly, we need to find the crowd distance of 1. So for, if I write here that for F2 this is xi minus 1 like that, so here we'll get the crowd distance for solution 1 is CD1 F1, so 0.79, so here 0.79, so we are doing 1 here, so that will be B, so B is at 0.79, so that is 0. This is 0.79 minus 0.27, maximum minus minimum, so it is 1.44. So here for the one distance is more, so 1 is selected. So for next iteration we have already selected front 1, and there infinite distance for 3 and B, and out of D and 1 count distance more, so 1 is selected. So that is for the next generation PT plus 1. Now from here we need to do the crossover mutations, and we'll get another 6 populations CQ2 plus 1, another 6 populations. So here then again we form RT plus 1, then we'll find the Pareto font, then we apply the algorithm, and again we calculate the crowd distance. So this will continue. So you can say that up to here first iteration is completed. We need to solve it for the next iterations. Now we are going to solve one question, which is that minimize f1, which is f1 equal to 10 plus x plus y, minimize f2 equal to 15 plus x into y. Here x lies from 0 to 15, y also lies from 0 to 15. So number of bits is required, that is 2 to the power n minus 1 greater than equal to b minus a by epsilon. Take epsilon equal to 1, so b minus a is 15, so 2 to the power n minus 1 greater than equal to 15, so 2 to the power n greater than equal to 16, n equal to 4. That means we need 4 bits for encoding. So here we assume the solution, the number name of the solution is a, b, c, d, e, f. So here for a, x is 2, y is 3, for b, x is 4, y is 5, for c, x is 1, y is 2. For D, x is 8, y is 9. For E, x is 6, y is 1. For F, x is 5, y is 1. So do the encoding for 2, 0, 0, 1, 0. For 3, 0, 0, 1, 1. Similarly, we have done all the encoding. So say check the last one. 5 it is 0, 1, 0, 1. 1 it is 0, 0, 0, 1. Now find the value of F1 and F2. So F1 is 10 plus x plus y. So it is 10 plus 2 plus 3, 15. 10 F2 is 15 plus 2 into 3, that is 15 plus 6, that is 21. Similarly, we have done all the we calculate the value of F1 and F2. So after crossover mutation, we obtain Q2. So Q2, the solution for we name the solution is 1, 2, 3, 4, 5, and 6. So here the solutions for 2, 1, for 3, for 2 it is 4, 7, for 3 it is 1, 1, for 4, 8, 10, for 6, for 5, 6, 1, for 6, 5, 1. So do the encoding part. So that is 0, 0, 1, 0, 0, 0, 1. Then value is 10 plus x plus y 13, 15 plus 2, 17. So in this way you calculate the value. Now we need to plot all the values in for the optimal front. So you can write here f1, you can write here f2. So f1 is a is 1521. So somewhere scale it. So check the next one. So we have plot these things. So that 10, 15. So the first is that 3. So 3 is the solution. Value is for 3 is the value here. 3 is 12, 16. So somewhere is 12 and 16 is here. So in this way we calculate all the values. So here we this is, you can say, front 1, this is front 2, front 3. So in this way for the next iteration solutions are 3C1. Then you can take the value of A, F, and the value somewhere 6 is here. So we take the value of 6. Now consider another questions which is that by using multi-objective genetic algorithm, basically NSGA-II, minimize the following function with 6 set of initial parent populations PT. We have to do binary encoding, single point crossover after the second bit of the chromosome from the end. So if we take on this chromosome, so from end, so we are considering here less significant bit, and with zero mutation probability, find the next set of solution only by obtaining parent optimal front and crowd distances if required. So minimize f1 xy is 30 plus x minus y. Minimize f2 xy is 10 plus xy. Here also x 0 to 15, y 0 to 15. So we need 4 bits. So consider 1, 2, 2, 3, 3, 5, 4, 6, 1, 1, 2, 8 as initial population, that is PT. So are given as f1 x1 is 30 plus xy, f2 xy is 10 plus xy. So our x for x1 is 0, 0, the 1 is there, so encoding it 0, 0, 0, 1. For 2, 0, 0, 1, 0. So in this way we have done all the encoding. So f1 is 30 plus x plus y, so that is 30 plus 1 minus 2, 29, and 10 plus xy, so 10 plus 2, that is 12. So in this way we have calculated all the values. Now we need to do the crossover after the second point from the end, so that is the chromosome x1 and x2, second point from the end. So this is the thing. So for x1 it is 0, 0, 0, 1, 0, 0, 1, 0. For x2 is 0, 0, 1, 0, 0, 0, 1, 1. So here the point. So x7 is 0, 0, 0, 1, 0, 0, 1, 1. For x8 is 0, 0, 1, 0, 0, 0, 1, 0. So that first 4 is x, next 4 is y. First 4 is x, next 4 is y. So here for x7, x is 1, y is 3. For x8, x is 2, y is also 2. Similarly for x2 and x3, so that is x2 0, 0, 1, 0, 0, 0, 1, 1. For x3 0, 0, 1, 1, 0, 1, 0, 1. So we got x9 as 0, 0, 1, 0, 0, 0, 0, 1. x10 is 0, 0, 1, 1, 0, 1, 1, 1. So it's represent 2, it is 1, and it is 3, it is 7. So that is x9 and x10. Now for x3 and x4, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 1, 0. So here x11 is 0, 0, 1, 1, 0, 1, 1, 0. and x12 is 0 1 0 0 0 1 0 1. So that is x, that is y. So here for x11 x is 3, y is 6. For x12 x is 4, y is 5. Again we calculate the value of f1 x1 and f2 x1. Now we need to plot all the values f1 and f2. So after plotting all the values, so you do it in fair copy, do it clearly, and there you will see, if you do it clearly you will see that the front is x7 x1 x5 x9 and front 2 is x2 x8. So these are the solution for the next iteration. From we got RT, so before conclusion just try to understand these things. From RT you will try to find the Pareto fronts and then apply the non-dominant sorting, non-dominated sorting. So apply that crowd distance mechanism, crowding distance mechanism, crowd distance, select 6 populations. So do this work. So in conclusion we can say that today we have understood some numerical examples by using NSGA-II. So question for today's class is that suppose minimize f1 xy equal to 30x plus 2 by y, f2 xy is equal to x square plus x by y into xy. Assume where x belongs to 0 to 15, y belongs to 0 to 15. Okay, so solve these questions up to solve this up to second iterations. So this is today's questions, and these are the references of today's class. Thank you.